this is Dance Lectures 256. Don't forget to like, subscribe, and follow. So we are still continuing with the various tests that you can run as a scientist to ascertain, to prove, to confirm whether the hypothesis that you are trying to validate is either right or wrong. To confirm whether the data you have makes meaning or it really doesn't make meaning. Last time we discussed a t-test, but we looked specifically at a one sample t-test, and we say t-test can be one sample or two sample. When say the one sample, I mean the two sample can either be a t-test for independent samples or a t-test for matched or paired samples. We say that the t-test for independent samples is used to compare means from two different samples. For example, if I collect, say I see fish from Lake Victoria and Lake Choga, and I want to find out whether they have the same average weight or whether they have the same mean weight, I just don't look and deduce. I must run a statistical test. And we said use a t-test to compare two means for data that has a homogeneous variance and data that gives a normal distribution. So today we are going to look at a t-test for independent samples. Say the t-test for independent samples is used to compare two sample means where the value of n is less than that, and we say t-test specifically compares two means, and we say the independence comes because one mean has no relationship with the other mean. The data is collected from different sources and there is no connection or linkage. So for our study today, we are going to use this example. However, before we start, the formula for a t-test for independent samples is as complicated as my name, which is mean 1 minus mean 2 over, or you divide by the square root of n1 minus 1 into standard deviation 1 squared plus n2 minus 1, the whole thing into standard deviation 2 squared. This will not be enough. Space won't be enough. I think I need to write it here. Formula is t is equal to mean 1 minus mean 2 over the square root of n1 minus 1, the whole thing into standard deviation 1 squared plus n2 minus 1 into standard deviation 2 squared over n1 plus n2 minus 2, the whole of this thing multiplied by n1 plus n2 divided by n1 times n2. So the square root of everything here. So that is our formula. Mean 1 minus mean 2 divided by the square root of n1 minus 1 times standard deviation squared, which in this case is our variance. In our introductory video, we said whenever you get the standard deviation and you square it, you obtain the variance. So it is n2 minus 1 still times the variance divided by n1 plus n2 minus 2 into multiplied by n1 plus n2 over n1 times n2. Still, the degree of freedom for a t-test for independent samples is n1 plus n2 minus 2. However, when you read some texts or when you read some books, it is written as n1 minus 1 plus n2 minus 1. So if you find such a thing, it still brings you back to this, because if I take out this one, it will be n1 plus n2 minus 2. Yes. Okay, with those two basics, we can now attack this question. So our question says, assess whether the mean length of the bird species is the same. Assess whether the mean length. That means we are comparing two means, and from this is our data that has been provided. You can see that the value of n is less than 30. Since I'm comparing two means, I already know that I'm using a t-test. So you see, sample 1 has 25 individuals, sample 2 has 25 individuals. Mean length, this is 18.5, this is 21.5.4. I have both standard deviations. We say you don't attack any statistics number by stating the null hypothesis, because it is the reason why you run the statistical test. So what is my hypothesis? That the mean length of the bird species, the mean length of the bird species is the same. The mean length of the bird species is the same. After stating my null hypothesis, I already know that this is a t-test. A t-test for independent samples. How do I know that it is a t-test for independent samples? Because sample 1 was collected from a different source and sample 2 was collected from a different source. So there is no relationship between the two. So after that, I come and then substituting in my formula. So to obtain my t calculated, so it will be 24. My mean 1 is 18.5. This is mean 1 and this is mean 2. This is standard deviation 1 and this is standard deviation 2. 18.5 minus 21.4. The whole of this thing divide by 24 times 0.4 exactly 24 minus 1 into 0.4 squared plus 24 minus 1 into 0.5 squared divided by 24 plus 24 minus 2 multiplied by 24 times, plus 24 divided by 24 times 24. Yeah, so you start pressing your calculator, chap, speed, 18.5 minus 21.4. I get negative 2.9. So negative 2.9 divided by whatever I'm going to get here. So 24 minus 1, get 23 times 0.4 squared plus 23 times 0.5 squared. You divide by 24 plus 24 is 48 minus 2, that is 46 times 24 plus 24, that is 48. You divide by 24 squared. I get my answer as square root of the answer. Don't forget to add the square root side after getting whatever you get. 0.131. Because I get 0.1307, I round off, I get 0.3131. So I get my negative 2.9 divided by 0.131. So I get negative 22.137. This is my t cal. We said you must get your t tab, or what they call the t critical value. Still, a t-test for independent samples utilizes the same tables as the one sample t-test, and we said it utilizes appendix 2, specifically the t-distribution table. So when you go there, I'll use 0.05. I'll read off at 0.05. If I check my tables, what do I have? Yes, I have 2.660 as my tabulated value, or as my critical value. We said you can see that the calculated value is way greater than the tabulated value. So you reject the null hypothesis. However, we say if you are not sure, you can come and draw your distribution curve and you indicate your critical value. This is also negative. I have negative 2.660 and positive 2.660. Then this side I have negative 22.137. So we said anything outside the critical value, you reject. So after this, you have to conclude, just like any other scientist, you must conclude at the beginning of this. You must conclude that. You conclude that the mean length of the bird species, in which one of the two has the largest in sample 2, in sample 2 is significantly larger than those in sample 1, and those in sample 1. What then you also add your calculated value, which is negative 22.137. What else? You add your degree of freedom. What is our degree of freedom in this case? We say degree of freedom is 24 plus 24 minus 2, giving us 46. So this is 46. And lastly, we say whenever you reject the null hypothesis, the probability is less than 0.055, because that is what I read off. Then I've used a t-test for independent samples. And that is how you go around with that number. We are still continuing. I want us to try out another example. Test the hypothesis that the mean length of leaves of indigenous and exotic mango species growing together is the same. Sorry, I forgot that. Is the same. And we said you don't carry out any test minus writing the null hypothesis. The null hypothesis is derived from the question. How do I derive it? The mean length of leaves of indigenous and exotic mango species growing together is the same. So I say my null hypothesis, the mean length of exotic and indigenous, I'll write this in short form, mango species is the same. So after writing it now, you're supposed to then know which test am I going to use. Definitely it's going to be a parametric test while we are comparing means. Which parametric test? That we say is dictated by the number of n. So if I count my n here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you can see that this is already 17. My n is equal to 17. Then this is 2 less. So that means here it is 15. So right now I'm going to use a t-test, but we're dealing with a t-test of independent samples. Why? The exotic trees grow alone and the indigenous trees grow alone. So there is no connection between the two. So it is a t-test for independent samples. So what do you do? Adding the discussion, they talked of an F test. So you can't just decide that such data has a normal distribution. The first thing you do is carry out an F test. Say the F test for homogeneity of variances, and the F test is equal to large variance out of small variance. I repeat, you should never decide on which test to use for such data, for such raw data, minus determine whether it has a homogeneous distribution, homogeneous variance or not. How do you do that? Use an F test to say the F test for homogeneity of data, homogeneity of variance. So, but when you realize that you don't have the variance, so what do? You organize your data like a scientist. You get the mean. You come and say indigenous, then exotic. Get the mean, get the standard deviation, which is S, and also get the variance, which is standard deviation squared. So from our video of how to use a calculator to obtain the standard deviation and mean, you enter the data faster, 19, 32, 26, 23, 29, 23, 22, 30, 19, 18, 23, 25, 35, 31, 21, 22, and 27. So what do I have as my mean for the indigenous one? Have 25.58. You press again shift 2. What do you get as the standard deviation? I have 5.32. You take the same procedure for the exotic one. What you get as your mean? I have 17.0. What you get as the standard deviation? 4.10. So we say variance is standard deviation squared. So you say 5.32 squared. You get 28.3. Then 4.10 squared, which is 16.81. So F is equal to 28.3, which is our larger variance, divided by 16.81. Let me see, 28.3 divided by the answer, I get 1.68, which is my F curve. So as we said earlier, this F test is used to test for normality of data or homogeneity of variances. So you need to also obtain the F tab. F tab is obtained from the tables, the statistical tables. We say there is a link in the description box directing you where you can get the tables. If not, you try to look for a book called Field by Statistics for biologists. Still the same tables are there. So the F critical or the F tabulated is found in Appendix 8 alongside the F distribution table. What is its degree of freedom? Table looks like this. We have F values this side. You have values this side and also have values this side. So what happens? You get n minus 1 for the larger variance, n minus 1 this side, n1 minus 1, then n2 minus 1. So I can decide to call this n1 and I can decide to call this n2, any that you want. So in this case, my n1 is 17, so it is 17 minus 1, which is equal to 16. This side I have 15 minus 1, which is equal to 14. So where 14 and 16 meet, that value is what I read off as my F curve or F critical. And from my tables here, my critical value is 2.84. I repeat, the critical value for F or F tab is found in Appendix 8 alongside the F in the F distribution table. Degree of freedom for the table is n1 minus 1 and n2 minus 1. What is n1? That will depend on your choice. So my critical value is 2.84. So you can see that the tabulated value is greater than the critical value. If I am to sketch this briefly, I have 2.84, then I have 1.68. So we say as long as anything falls here, you accept the null hypothesis. But the F test tests for homogeneity of variance or normality of data. So whenever you accept the null hypothesis, that means our data is normally distributed. Data is normally distributed. Or this is the same as variance 1 is equal to variance 2. That is what it basically means. However, you can do a test and your F tab is less than the F cal. There are things that you do there that we shall be seeing later. So, since we found out that our data is normally distributed, or our data shows a normal distribution curve, then you can proceed to do an AT test for independent samples. So you substitute into our formula, which was T is equal to mean 1 minus mean 2, minus mean 2 out of the square root of n1 minus 1 into standard deviation squared plus n2 minus 1 into standard deviation 2 squared out of n1 plus n2 minus 2, the whole of this thing multiplied by n1 plus n2 out of n1 times n2. Yeah, this is our formula. So if you are to substitute in, it will be now T is equal to what was my mean 1, 25.58 plus minus 17.0 divided by the square root of what was my n here, 17 minus 1 into what was my standard deviation squared here, 28.3 plus what was my n here, 15 minus 1, the whole of these things, standard deviation squared, I got 16.81 divided by 17 plus 15 minus 2, the whole of this thing multiplied by 17 plus 15 out of 17 times 15. Please don't forget everything, it is very important. So we start doing our calculations. Another thing important to note, whenever you are pressing in this value, you take one at a time. Otherwise, you might end up mixing things. So 25.58 minus 17.0, I get 8.58. Divided by whatever I'm going to get here. 17 minus 1 is equal to 16. I hope you're also calculating. Good. 16 times 28.3 plus 14 times plus 14 times 16.8 divided by 17 plus 15, that gives us 32 minus 2, that is 30 divided by 30 times 17 plus 50, so I get 32 divided by brackets again, 17 times 15 close brackets, I obtain 2.87. The square root of the answer is 1.69. So I say 8.58 divided by the answer, I get 5.057, and this becomes my T tab. Then I'm supposed to get my T tab. We say T tab is found on my T tab is found on appendix to the T distribution table. If I check my table here at 0.05, my critical value becomes a minute. So far it comes. Still looking, and also checking. Yes, at 0.05 it becomes 2.705. 2.705. I've read off at 0.05. And we say degree of freedom is this one down here. N1 plus N2 minus 2. So these two, when I compare, the calculated value is greater than the tabulated value. Therefore, we say you reject a null hypothesis. You come and conclude as such by saying that the mean length of which of the two has a larger mean of the indigenous trees, of the indigenous leaves, actually mango leaves is, don't forget the word significantly, because you can face a very big difference in mean. Significantly larger than those of the exotic leaves. Please don't forget to specify your t value, which you've calculated 5.05. Don't forget to include your degrees of freedom, which is, we said 17 plus 15 gives us 32 minus 2, which is 30. Since we rejected our null hypothesis, the probability is less than 0.05, and I've used a t-test for independent samples. T-test for independent samples. And that is how you conclude. T-test for independent of a t-test for independent samples. And in this case, they're telling us to assess whether the abundance of the woodland kingfishers at 8 different sites is the same in 2 habitat types. Question is assess whether the abundance of the woodland kingfisher at 8 different sites in 2 habitat types is the same. What are the habitat types? Woodland and forest. First of all, you can see that the value of our n is less than 30. N is less than 30. So that tells you that you're supposed to use either a t-test or its analogies. So what do? We say any sort of such data, the secret data, we're supposed to first count and test to find out whether the data has a normal distribution or it is skewed. So how do you do that? We say you carry out an F test. We say F is equal to large variance over small variance. But in this case, we don't have the variances. We say you go to your calculator and obtain the standard deviation of both the woodland and the forest. Woodland and the forest, still obtain the variance and the mean. So how you get your calculator, I hope you're doing as I'm doing. You add 8 m plus 12 m plus 15 m plus and the likes up to when you get both the standard deviations and averages for both. So in this case, my standard deviation is, let me see, 18.58, and this one is 6.08. So 18.58 squared is 345.2. Then 6.08 squared is 36.96. So I'll get the mean in case I find out that the data is normally distributed. If it is skewed, I don't need the mean. So I first square out my f-test. We said it's large variance, which is 345.2. You divide by 36.96. 345.2 divided by my answer, I get 9.3 4 as my f curve. We said you were supposed to get your f tab. F tab degree of freedom, we say if this is our f distribution table, appendix 8, this is n minus 1, n1 minus, n2 minus 1, n1 minus 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1 giving us 7. This side also have 7. So have 7. Where 7 and 7 meet is the value that I read of checking from my tables here. My f curve, f tab is 4.99. So still we said if in case you're not sure whether to get another hypothesis or not, you draw a distribution curve. My critical value is 4.99. This is also 4.99. So I say read off the f value from appendix 8, which is the f distribution table. So I have 9.34, which is around this side. So that means my data is not normally distributed. Data is not normally distributed. Data not normally distributed. Data not normally distributed. So what happens in this case when you find out that data is not normally distributed? You have two options. You either transform the data in what they call logarithmic transformation, or you use a non-parametric test, But since, and we said after the logarithmic transformation, the data will become now normally distributed, and you can use a parametric test. But since we are discussing today the f test, we shall transform the data using logarithmic transformations, so that we can use a t-test for independent samples. Why independent samples? The number of woodland kingfishers in the woodland have no relationship or have no connection with those ones in the forest. That's why it's an independent t-test. So what do I mean by logarithmic samples? You go to your calculator, you press log of this number, log of 8, and this is what you will get. You come and press log of 12, You redraw the same table, this is what you will get. You press log of 15, this is what you will get. The same thing with the forest, log of 12, this is what you will get. Log of 4, this is what you will get. So you do that for all the 8 different samples. You do it for this one, do it for this one, do it for this one, up to when you have transformed all them into base 10. So from here, our data will have a normal distribution curve. If you want to confirm that, you can do another f test. But that is not important. It's not important, but in case you want to do it, please do it. So what happens? We've transformed our data, so we can use now a parametric test. Initially, this data was skewed, so it did not have a homogeneous variance, so it did not have a normal distribution curve. That is why we had to transform it. You don't just transform it, and how we confirm that from the f test, and we say whenever the calculated value is greater than the tabulated value for the fertility test, data is skewed, or data has no normal distribution curve. So you have to transform it or use a non-parametric test, which is what we shall discuss later. So from here, you can now use our t-test. We say it is equal to mean 1 minus mean 2 out of the square root of n1 minus 1 into standard deviation 1 squared plus n plus n2 minus 1 into standard deviation squared out of n1 plus n2 minus 2, and all of this thing multiplied by n1 plus n2 minus n1 times n2. Divided by n1 times n2. So what happens here? You get the mean for this thing. You get the mean for this thing and you get the mean for this thing alongside its standard deviation. So you come and say woodland, then forest. Forest, you get the mean, you get the standard deviation. From my calculations here, I have 1.37, then I have 0.94. Very important to note here, you get the means of these values that you have formed after transformation, not this initial set of data. Please take note. Please take note. So, and my standard deviation, I mean, sorry, this is supposed to be a 0.94. My standard deviation is 0.137, and this is 0.4. So it's better if you get the variance once and for all. This is 0.10 and this is 0.16. You can please confirm with your own colleagues that side. So you come and substitute in here 1.37 minus 0.94 over 8 minus 1 is 7 times what is my square? 0.1 plus 8 minus 1 is 7 times 0.16 over 8 plus 8, which is 16, minus 2, that gives us 14, into 8 plus 8, that is 16 out of 60, for which is 8 times 8. So when you press that on your calc, you get 0.75. You can confirm it briefly. 1.37 minus 0.94, you get 0.43. Then 7 times 0.1 plus 7 times 0.16 divided by 14 times 16 divided by 64 is part of the answer. This gives us 0.180, so 0.43 divided by the answer, I get 2.38 as my T curve. So from here we say you move directly to your T tables. Appendix 2, the T distribution table. We say we use the two-tailed test. The two-tailed test, I'll read off my value at 0.05. So when I check my tables here to obtain the calculated value, I get a degree of freedom, say n1 plus n2 minus 2, which gives us 14. So I get my critical value or my tabulated value when I read off at 0.01 is 2. My T tab is 2.97. But that our calculated value is less than our tabulated value. From our distribution curve here, we say the probability of 0.01, my calculated value is 2.97, yet I have 2.38 as my calculated value. Therefore, I accept the null hypothesis. You say anything that lies within the curve, you accept. Anything outside the curve, you reject. Therefore, I come back and conclude that the abundance of the woodland kingfishers, abundance of the woodland kingfishers, woodland kingfisher at 8 different sites is the same. Right, the T value T is equal to 2.38. What else? My degree of freedom is equal to what do we get? 14. Then probability is greater than 0.01. We said whenever I reject the null hypothesis, the probability is less. Whenever I accept the null hypothesis, the probability is greater. Then we use a T test for independent samples, a t-test for independent samples, a t-test for independent samples, test for independent samples. I forgot to state the null hypothesis as I was starting. The null hypothesis was the abundance of the woodland kingfisher at 8 different sites in 2 habitat types is the same, which is what we have accepted here. Otherwise,